Okay, welcome to note set number 21, where we'll see how to use the DFT to implement FIR filters. Later in the course we'll get into the design of FIR filters, and we'll see a lot of the characteristics that make them very desirable. They are by far the most widely applied type of filter, and the reason that we're going to look at implementing them via the DFT is because if we use the FFT algorithm, which we'll also study in upcoming note sets, we can compute the DFT very efficiently, and even though at first blush it might seem like we're making things more complicated, actually the amount of complexity, so the number of multiplies and additions that we have to do to compute the output of the filter is actually less under certain circumstances if we do it this way. So we're covering things that are in section 7.3 of the textbook, and so you ought to be focusing your reading there. Would like to just point out in passing that this is our first exposure to using the DFT in some sort of algorithm, and it's a widely used tool within various signal processing algorithms. We've previously alluded to it just as a signal analysis tool, but now we're going to look at it as a means for implementing a particular type of discrete time system. So here's the motivation. From the analysis point of view, we know that we can model or interpret what a linear time invariant system does in the time domain as convolution, and in the frequency domain we can, by the convolution property, represent the effect of convolution as a multiplication in the frequency domain. So rather than convolving an impulse response with an input signal, what we do is we take the frequency response and multiply it times the DTFT, and here you can see I'm using theta as my discrete time frequency variable. So these were notes that I used originally with the Peratt book, which uses theta. So we do that multiplication, and we get the output DTFT, and then if we can transform it back to the time domain, we could get y of n out of that. And it's a really nice thing to do for analysis. And we also think that way for the design of our filters. When we get into the design of filters, we'll be talking about what is the pass band, what's the stop band, talk about the linearity of the phase, and so forth. But the question is, could we actually implement the filter over in the frequency domain? So could we somehow compute these two things, form the product, and then do the inverse transform to get back to the time domain? And the bottom line is that no, we can't really do that for actual implementation, because the DTFT is defined at infinitely many points from minus pi to pi, and so we can't really compute the DTFT. So we've made that argument before when we introduced the DFT, and we said, well, gee, couldn't we just compute this at a appropriately fine grid of frequency points and do it that way? Well, that's a good question, and that's the kind of question that DSP engineers ask all the time. Could we? Well, we can't just jump to the conclusion that it will work. We have to analyze it and determine, will it work? And so that's what we will do. So the question is, does this work if we switch to a DFT? And we can only do that if the input signal is going to be finite length, which, in the real world, all input signals start and stop someplace. You just may not know when they're going to start and when they're going to stop. But in principle, they're all finite length. So in principle, we could compute the DFT of the input. And likewise, if we limit ourselves to FIR filters, then our filter impulse response is finite length. One might think that we could do the following. We would imagine that we have, and just for the purpose of discussion here, let's say that we have length n filter and a length n signal. That way they both end up having FFTs computed, or DFTs computed, that are both endpoint DFTs. So we would compute this DFT of our input signal, and I don't show it here, but we would compute our DFT of the impulse response. And then this box here forms the product, and then we would do an inverse DFT. And the question is, do we get what we want, even for this simple case? And the answer, well, we'll see in the slides. And so the first answer is, well, not necessarily. And as we've already seen in our DFT theory, if you take the product of two DFTs and then do an inverse DFT on them, what you get is not regular convolution, you get circular convolution. So the block diagram that we just looked at does not give us the ordinary convolution that we want. And so at first blush it looks like, no, this is not going to work. But again, as good DSP development engineers, we ask, well, could it work? Could we fix it so that it does work? Are there any tricks that we could use? Let's understand why this gives us circular convolution. Let's explore it, understand the machinery of it, and maybe we can make it work. And in fact, there is a trick that we can apply that will make this give us the linear convolution that we really want. And so we ask another question: when does cyclic convolution equal linear convolution? And I'm a firm believer in using examples to explore and understand. So let's take a look at an example to see how this works. So let's first look at what linear convolution does. So here's two original signals, and here we're actually allowing them to have a few zeros at the end. So we have x1, which is length 9, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're not including the zeros at the end of that one, well, yeah, I guess we don't have to really talk about including the zeros at the end or not. H is a length 5, 1, 2, 3, 4, 5. And so if we were going to do this with DFTs, we would imagine taking that all the way out to the same length n, equal to 9 as x is. Then we would take a 9-point DFT, do the product, and then inverse DFT it, and we would get circular convolution. But here we're exploring the effect of linear convolution. So let's just see what we get when we linearly convolve these. So our rule is we write one of them against a dummy variable. So that's really no different than just changing n here and here into m here and here. So we have that. And let me see if I can get rid of that. I bet it won't let me do it. Nope, it does not. All right, do it that way. So we've got x written in the dummy variable m. We've got h written as m, and then we flip it. So that's why we have the negative m there. So once we flip it, we just anchor it here and flip everything over. So it's just like flipping it out of the page, anchored there like a hinge almost. And so these are the two signals that we need to do to compute linear convolution. And if you think back to how linear convolution works, we do the flip, we have to do various shifts, and at each shift we multiply the top times the bottom, and then add up all those products, and that gives us the output at the n value corresponding to the shift. So if I want to find my n equal to 0 output, I don't do any shift at all. So I just flip, and then no shift, and multiply, add up all the results, all the products, and that gives me my output at n equal to 0. So so here I see that I only get these two interacting. All of these zeros nuke those, and all these zeros nuke those. And so that's what I get. Now notice also though that if we can claim that our output is 0 for any negative n, because a negative n would correspond to a shift to the left of this. And so if we shifted this to the left, then we would have no non-zero products of the two signals. So we would say that there's no overlap between the non-zero parts of those two signals if we shift to the left. If we shift to the right, that would be for n equal to 1, n equal to 2, n equal to 3. We can see that this thing is going to start moving through, and eventually we will get to a point where this last one is aligned with this one, and that'll be the last non-zero output point. So if next slide, that's exactly where we are. And for this case, if we take n1 plus n2, and then minus 2, that gives us n equal to 12. That's the last output point. So at little n equal to 12, we would get those two things multiplied times each other, a bunch of zeros, another bunch of zeros, add up all those things, and we'll get we'll get a non-zero output sample. That's our last non-zero output sample. And then if I shift this one more to the right, then all of this is lined up with all of these zeros, and all of these zeros are lined up with those. So we get no more non-zero output points. So what we find is, looking at that amount of stuff tells us kind of how this linear convolution works. We don't necessarily have to work out what every output looks like, but we know that we're going to end up having 13 non-zero output samples for n equal to 0 out to 12. So in general, if we're convolving something that's length n1 with something that's length n2, the length of the output after linear convolution will be n1 plus n2 minus 1. So we just demonstrated that for this case, and we can show that that's true in general. So let's keep that in mind now as next slide and think about cyclic convolution. So when we talked about the DFT property of multiplication and then transforming back, we talked about what cyclic convolution does. And one of the ways we talked about it was in the context of periodizing the signal. So in this case, we're going to zero pad the shorter signal out to the length of the longer one. Excuse me. So we have to do that so that the resulting DFTs are the same length. So in this case, we'd have a 9-point DFT. We would form the product, take the inverse DFT, and now we'll analyze cyclic convolution to see how it works, to see what we get. So to see how cyclic convolution directly works, we take this periodized version of these two signals, and we flip one of them. So I'm going to flip the same one, so the bottom one corresponds to the shorter sequence, and that I think was our H signal, our impulse response. I'm going to flip the periodized one around this point, so I'm going to anchor that point and flip it. So down here, the bottom one is now the flipped version of that, and you can see that when I did that, this orange one ends up over here now. And so notice that that interacts with some of the blue ones. Now that stuff was not present in my flip for regular convolution, and so now we have something new here that that didn't show up. And so we're starting to see why circular convolution is not equal to regular convolution. So we're seeing one aspect of it anyway. But nonetheless, to see another aspect of it, let's imagine so we didn't do any shift, so that's our n equal to 0 output. So we would form the product and sum over one cycle. That's the rule for doing circular convolution, just sum over one cycle. So we're going to sum up these products. So I did not take this last point here, which is the start of the next cycle. So I'll have one non-zero product at the beginning. That's the correct one, correct meaning the same as the linear convolution. And then I have 4 non-zero products over here that get thrown into the sum and give me a value that is not the same as what I would get for the linear convolution. So that's for n equal to 0. And then if we proceed on the next slide, let's suppose that we now proceed to n equal to 8 and see what ends up happening there. So now I'm going to take this periodized and flipped signal, shift it to the right by 8, and if you look carefully, you'll see that we get something that looks like this. Now in that case, we can verify that this looks exactly like what we had as linear convolution. So the n equal to 8 output sample is correct. The n equal to 0 output sample was not correct. Now, one final thing to see that's different about circular convolution or cyclic convolution and linear convolution is, let's imagine that we try to go out to n equal to 9. One more step further, so we shift this to the right, and if we look carefully at that, we will see that the green one now shifts in and starts to play the role that the blue one had. The blue one now starts to play the role that the orange one had, and in fact what we see is that the scenario with a shift of 9 is exactly the same as a shift of 0. So if we were to compute the circular convolution for n equal to 9, we would get the same exact value that we had for n equal to 0. So what that tells us is that the output is also a periodically extended signal. And so that differs from what we see for linear convolution, which is not periodically extended. And we also are missing some of the output samples, right? Remember, for linear convolution, we went from n equal to 0 out to n equal to 12. Well, we got out to n equal to 8. Some of those outputs were correct, some of them were incorrect. But if we try to get the remaining ones, 9, 10, 11, and 12, we won't get the correct things because we are wrapping back to the beginning. We're getting the same as we got for n equal to 0, which was wrong, n equal to 1, which was wrong, and so on. So in general, we can see that the length of cyclic convolution, the output is just the maximum of the two lengths, and that's assuming that we follow the rule that the shortest one is 0 padded out to the length of the longest one. So clearly, if we were to do this DFT-based multiplication and then inverse DFT, the thing that we get is absolutely not the right thing. But we're starting to see maybe a way that we can spoof this by using some 0 padding. So let's take at how that might work. So how can we make cyclic convolution equal linear convolution? What we've seen is that some of the output values are different from what linear convolution gives us. Some of them are the same. And the length is also not correct. So if we go back to that example, you can actually verify that if you choose a number k, which is bigger than n1 plus n2 minus n1, and remember, that is the length of a linear convolution. So what we're doing is we're choosing a number k, which is bigger than the length that we expect from the linear convolution of the two individual sequences. And then we're going to zero pad each signal out to that longer length k. So N1 is going to have N2, at least N2 minus 1 zeros added onto it. And the signal with length N2 will have at least N1 minus 1 zeros added onto it. And so with those zero padded signals, we will now periodize that to this length k segment and do the circular convolution. And my claim is that this will actually, if you take out the k output samples from this, you will see that they are exactly equal to the values that you would get from a linear convolution. And I'm just asking that you verify that yourself rather than having me go through it here. Just do it with this simple example. You can go through and verify that to yourself. Okay, so now we're armed with a way to make this DFT-based frequency domain implementation of FIR filtering actually work. So we've got some impulse response here that's length N2. We've got some signal block that's length N1. We tack on some zeros at the end of each of them. Different number of zeros at the end of each one for the case where N2 and N1 are different from each other. And we zero pad both of them out to the same length, some length k, and the only requirement is that it be at least as long as the linear convolution between x and h. And so once we do that, we then compute the k-point DFT, of the impulse response. And I'm alluding here that we will do this with the FFT, which we'll be studying soon, and is an efficient way to compute the DFT. And also point out that, look, this filter is something that we're trying to design and implement ahead of time. So, in reality, we can pre-compute one of these two DFT results. So so that saves some computation. We don't have to count that against ourselves. So really, the only computation we would have to do would be compute this k-point DFT, compute these k products, compute a k-point IFFT, and we get a bunch of samples, k samples, and we'll take those as our output. Now, if we picked k strictly greater than this number, there will be some zeros at the end, and we can ignore them. So however much k is bigger than n1 plus n2 minus 1, that's how many zeros we'll have at the end that can be ignored. So you can throw those away if you want, or you can just leave them there and they're valid. That is what would happen if we linearly convolved this finite duration x with this finite duration h. And so now down here at the bottom we've got this question. Why do we do this? Well, it's clever. It's kind of interesting. It shows that the DFT can be pressed into service to do things that are reminiscent of what we do in our analysis viewpoint. But we will see in just a few slides, even though we don't really know the details of the FFT, we can use a pretty famous result about the FFT complexity to show that in many cases, even though this looks more complicated than just simply doing a convolution or a direct form 2 block diagram for an FIR filter, in many cases, and we'll clarify which cases we mean, this will actually be less computationally expensive than doing it directly. So it's a nice trick to keep up your sleeve in case you need it. Now, this complexity only counts things like multiplications and additions. It doesn't count things like, well, I have to do this many more memory accesses, or I have this much additional control logic in my code. So, in the real world, those things do count, and you can only make assessments on those based upon the characteristics of specific computing environments. So we can't make general rules about this, but the bottom line is that for some cases this will come out ahead, even if you take into account all of those real world things. The trick is to being able to analyze your computing environment to know precisely when you should do this and when you shouldn't. Now, when I was working, quote unquote, in the real world, I provided the DSP insight, and then I worked carefully with, the computer engineers who would be able to help and collaborate with how to determine what the break-even point was on this and whether it was feasible to do it. But there are people who are both equally knowledgeable in DSP and computer architecture, and they can do all that themselves. I'm just not one of those, and I don't know which side you're aiming for. Maybe you're a computer architecture person who's just picking up DSP as kind of a secondary thing. Well, you'd be in a really good position to collaborate with a DSP expert now that you know a little bit about this. All right, so let's move on to the next slide. So we just got done saying, wow, how great is this? Now we're going to start knocking it down. And again, this is how good DSP developers, good DSP researchers operate. We say, hey, could we? Doesn't seem to work. Well, maybe we can make it work. Yes, we figured out how to make it work. What are the problems? What could go wrong? What's bad about this? What's good about it? When does it work? When doesn't it work? And so let's throw a problem at it. What if, remember, N1 and N2 are the lengths of the sequences, and we've been using N2 to be the length of the filter. N1 is the length of the signal that we need to filter. So what if N1 is really, really big compared to N2? Well, for one thing, we would need to do an FFT that would be at least N1 plus N2 minus 1. And since N1 is really big, that means that we have to do a really big FFT. And so that might be too big for our computational power of our processor, not to mention the memory that we have available. And so that's one issue. The second issue is that we can't get any output samples until we've consumed the whole signal. So imagine, that you suddenly decide, oh, here's a song that I'm listening to. It's 5 minutes long, and you decide I want to filter this to do a little bit of tone control on it, and I'm going to use a filter that's implemented this way. Well, you won't be able to hear any of the results until after you've essentially taken that whole song and processed it through your filters. Then and only then will you be able to even hear the very first sample. So here's another example. Suppose I only want to so this is the big FFT part. Suppose I have to filter 0.2 seconds of a radar signal. My sampling rate is 50 megahertz. So my N1 is going to be 10 to the 7th samples. So my FFT is going to be bigger than 10 megasamples. And that's a really, really big FFT. And then this is the issue with the, filtering a stream of audio. So my FFT size can't be set ahead of time, and I have to wait until the entire audio stream comes in. Then I can start to get, then I can start to do processing, and some short time after that, due to delay of computation, I can start to get the first output sample. So things were looking good for a while. It looked like this might be a good scheme. Well, there must be a fix to this, otherwise we wouldn't be talking about it. And in fact, there's a fix to that. So here's a better way to do this, and there's a couple different ways of doing this. The two common ways of doing this are called overlap add, which is called OLA, and overlap save, or OLS. And I'm going to cover overlap add. Both are covered in the textbook. They're both very similar, although there are differences in them. And pretty much if you understand how overlap add works, you can always go back and should be able to understand overlap save. So you don't really have to study both of them per se. There are some pros and cons to one or the other, but no one, it's not like one, you need to know one for one case and one for the other case. There may be some architecture specific reasons for preferring one or the other, but again, I'm not a computer architecture person, so I don't really know the answer to that. So nonetheless, we will talk about overlap add here. Now both of these methods exploit the idea of linearity. So if I can break up my input into a sum of blocks, then what I can do is process each one of these blocks individually. So if I filter one block, then I can take the output of that, filter another block, take the output of that, and since the total input is made by adding together the blocks, all I have to do is add together my outputs. So the difference between OLA and OLS lies in how these blocks are formed, and I'm really going to focus on the method here for overlap add. So, however I end up creating these little individual blocks, I can convolve each xi with h to get some output zi of n, and since the input is a sum of the xi's, the total output is just a sum of the zi's. So that's the basic idea. And for overlap add, we pick these blocks in a very simple way. They are non-overlapped, but the blocks are contiguous, meaning there's no gaps between the blocks. And so this is just a fancy equation here. Our block length will be NB. And basically, all we're doing is we're saying xi of n. So here's xi of n, and illustrated here with a figure from Peratt's book. So it's just the stuff within these boundaries, but then zero otherwise. So we assume that for each block, there are zeros everywhere else. And that's the part that allows us to just simply add them together. So on the previous page, we had x of n was equal to the sum over all the I of x sub I of n. So each one of these blocks is zero where the other ones are non-zero, and so it's pretty easy to visualize them all. Each one of these blocks lined up with no non-zero values overlapping, and then you add them all up, and it gives you exactly what you want. And so this little business here, I NB out to I plus 1 NB. So I is just going through the integers. So when you start with I equal to 0, you're going from 0 up to just shy of NB. Then you flip to I equal to 1, and so now you're going from NB, which is the very next sample, up to just one sample shy of 2 NB, and so on, and so on, and so on. And so that's what we're showing here, and we're just showing three such blocks. Okay, so we chop up our input signal that way. We know that those blocks sum to give the input signal. So all we have to do is look at each one of these little chunks and imagine it as a finite duration chunk that's going through the filter to create an output, and then we just have to align that output correctly relative to all the others and add them all up, and that's the basic idea of the algorithm. So what happens when we take one of these input blocks and convolve it with a length n2 filter? So let's take this block here, which we're showing has 5 samples. Now, when we convolve, now we're going to do this convolution using the trick with DFT processing, but we're making sure that the trick is set up with zero padding so that we get the appropriate linear convolution. So to understand what's going on here, it doesn't matter how we compute the linear convolution, just that we visualize that we are computing the linear convolution. So we're just going to imagine what the result looks like, but the reality is that each one of these blocks gets convolved with the filter using a using the little trick that we saw on a previous slide that allows the DFT based filtering to give us linear convolution. Well, we know that linear convolution will expand the length of the input signal. So in our example here, our input block is 5 samples and the corresponding output block looks like this. Now we're assuming it's a causal filter that has a non-zero output immediately when the first non-zero input comes. So the first output sample is going to be aligned with the first input sample of that block, and then eventually we end up getting some number of points that goes beyond the boundary of the block. But that's fine. That's the output due to the linear convolution computed using products of DFTs. Now Peratt uses this notation of U and V, and I ignore that. I don't really need it for my discussion. But this thing is this quantity that I've computed here is the Z I minus 1. It's just for some I. So then I go to the next block, which is the ith block, and it will create a output. It starts aligned with the first input sample of that block, which aligns with the part that hangs over from the previous block. So this is where the overlap term comes from. So what do I need to do? I need to take the output from the ith block, put it in the correct position, which will overlap some number of points, and you can easily figure out how many points it will overlap based upon the length of the convolution. But basically you're putting it in the very next sample after the end of the previous input sample block. So you just index that properly, put it into the proper place. It will overlap here, and now we're just going to add these values with these values. And so at this point, all those values within the ith block index can all be added together at this point. So we're adding to the output from the ith block the hangers-on from the I minus 1 block. And so that's what we're doing. And we just keep proceeding like this. We then take the I plus 1 block, this part gets computed, and we add into it the hangers-on from the ith block, and so on, and so on, and so on. And so if we do this, and we keep adding these things all up, you'll notice that we only ever have contributions from 2 adjacent blocks at any one time. So, so once we've computed the output from the I minus 1 block and the output from the ith block, we can add all of these things together and we get all the output samples for that region. And then we just continue on like that. And so that's how this thing works. And that's why it's called overlap add. Let's go on to the next slide. And so this just summarizes the steps that we have to go through. So we've got some filter impulse response h of n with a length n2 that's specified. So based upon that, we need to choose a block size, and we'll talk about what drives the choice of that in just a little bit. Then we have to choose an FFT size. So that's going to be the where we need to account for the zero padding to make the DFT based product filter method implement linear convolution. So we've got NB as our block size. That's like our input size. That's playing the role of N1 from our earlier discussion. N2 is our filter size. So we need to look at NB plus N2 minus 1. That's the smallest that I can make my FFT. Now FFTs work best, as we'll see, with the standard algorithms anyway, when their length is a power of 2. So we'll pick some power of 2, 2 to the p, that is at least as big as NB plus N2 minus 1. So we pick that equal to some power of 2, and that helps us out in the complexity. So I say see below. We'll discuss that issue when we talk about the FFT later. So that's all setting things up. So the choice of block size, the choice of FFT size is all done when you're designing and implementing this scheme. And so then when we want to run this, I put this first step in the running, even though that would really be something that you would do just once. So I zero pad h of n out to my FFT size, and I compute the nFFT point FFT of that, and I comment here that that can be pre-computed, and so we don't count that against our real-time complexity in any way. And now we start the actual processing. So that was done ahead of time, and that result is stored and kept there. I don't have to do that FFT ever again. Now for each block, so I get a block in, and the big thing I'm going to do is compute the output z sub I of n. That is an appropriate linear convolution of the block with this filter, h of n. And I'm going to do it using the simple DFT-based method. And so I've outlined the sub-steps to do that with the little triangles there. And so the steps that I have to do are I take my block, which was NB long, and I zero pad it out to nFFT long, and I compute the nFFT point FFT of that. I then take that computed FFT and I multiply it by the FFT that I computed of H. So that's this next step. I take that product, I compute an IFFT that will give me Zi of n. I appropriately overlap that with the previously computed output block. So in other words, I just take the first sample of this and I line it up with the first sample in my input block. I just add it to my output buffer. Now that output buffer may already include the hangers-on from the previously computed block. If this is not the first block, obviously in the first block there's nothing there, so I just there's no hangers-on, so I just put it in there and I'm done with it. Second block, I have to align it properly with the hangers-on from the previous block and then add them together. And then I go back up to the top and I do this all again. I do it again for the next block and for the next block and for the next block. So very, very simple processing scheme. And so this is really cool, and it works really, really well. So try to figure out what is the complexity of this and when should we use this and when shouldn't we use this. So I know that we haven't really talked about the FFT yet, but we'll use a classic result here, actually two classic results that tell us how many multiplies we need to do. And all we're going to do is count how many multiplies do we have to do for each input sample. Now I know the input samples are coming in blocks, but it's like, suppose you we're thinking about bags of sand. I'm thinking about bags of sand only because a couple days ago there was flash flooding here, and I was battling a torrent of water in my backyard, and I was really wishing I had sandbags. So suppose I get 20 bags of sand and I have to pay $100 for those. Even though they're coming in 20 bags at a time, I can figure out how many dollars per bag. Same kind of thing. Even though my input samples are coming in blocks and I'm doing all this block processing, once I find out how many multiplies I have to do for a block, I just divide by how many input samples there were in a block, and I get number of multiplies per input sample. So it's just a common way of normalizing your complexity count. I could just as easily have done, or just as convincingly done, this number of multiplies per output sample. And I would do it in a similar kind of way, but sometimes it's more convenient to reference complexity versus input sample versus complexity versus each output sample. So anyway, that's how we're going to measure it, and we're only going to count multiplies, which is a common thing. Typically, if you look at the number of multiplies, it will give you a good feeling for how one algorithm compares to another. To be a little bit more precise and complete, we really should look at the number of multiplies per input sample and the number of additions per input sample, and look at both of those, and then look to see how much time it takes to do each multiply and how much time it takes to do each addition. I will say that historically people have focused more on multiplies because in the old days each multiply took multiple cycles to do, whereas an addition took a single cycle. So it's like, suppose you're measuring the length of tent poles and tent stakes. Well, if tent poles are 10 feet long and tent stakes are 5 inches long, you really only need to focus on total length of tent poles. If you're trying to get a total length laying end to end of all tent poles and all tent stakes, it's not exact, but the scenario that will minimize the number of tent poles will win out. Okay, so the other thing that we're going to use is we need to know how many multiplies it takes to do an FFT of length NFFT, and so there are some tricks, and we'll talk about those later on when we get into the FFT algorithm. But if we assume that our input signals are real valued, which is generally the case, not always, remember our complex equivalent low-pass signal. But for the most part, let's assume, just as an assessment here, assume that our signals are real valued. And so there's a trick. You can actually trick an FFT, which is designed to work on complex numbers. You can put two real signals into it. One is the real part, one is the imaginary part, and be able to actually compute the FFT of two different real signals for the cost of one complex FFT. And so this is a classic result that people have found and discussed in textbooks. So so using that together with the cost, the typical cost of a complex FFT, we will say that we need to do 2 times NFFT log 2 of NFFT. So this is the famous n log n result for the FFT. Maybe you've heard that, and this has just been adjusted to account for this, and we're counting real multiplies, not complex multiplies. So that's going to be our measure of the complexity of an FFT, which is where we're doing all of our heavy lifting here. So for each pair of input blocks, so I say each pair because we can do 2 real signal FFTs. So what we're going to do is take a block, take another block, put them both into a single FFT, and compute them that way. Causes a little bit more latency, but it reduces the complexity. So that would be a trade-off that someone could look at if they needed to. So for each pair of input blocks, we need to compute one FFT, and we've already said that'll take 2 NFFT times log 2 NFFT real multiplies. So that's computing the FFT of 2 input blocks. Then we have to do a product, and so we have to multiply the DFT of each block times the DFT of the filter, and we're doing that for a pair of input blocks, so we end up with 4 NFFT real multiplies. And then we have to do one inverse FFT, and again, that's using this trick, same trick as we used. We can do one complex FFT and essentially get 2 output blocks that way. So that will cost us 2 NFFT log 2 NFFT real multiplies. And if we add that all up, we get something that looks like this, where we've now replaced NFFT by the smallest possible value, ignoring the fact that it would be 0 padded up to the next higher power of 2, but we'll ignore that for right now. So that's our total number of real multiplies that we need to do, and that number of multiplies is spread across 2 blocks. So each block has NB. So this is like the $100, and this is like my 20 sandbags. And so now I'm going to take my $100 divided by my 20 sandbags and find out dollars per sandbag. And so here is that quantity. So I've just taken this quantity here. The NB from here is dividing right there. So that's the number of multiplies per input sample. Next slide, and we need to compare this to doing the time domain method. So our filter has length of N2, and therefore, assuming that this filter doesn't have some symmetry aspects, which we'll see later on that good FIR filter designs typically have some sort of symmetry, which means that we could cut the number of multiplies in half, exploiting that symmetry. But we're going to assume that there is no symmetry here. So for each output sample, we would need to do N2 multiply, since we have N2 impulse response values. Just imagine computing the output of each, an output sample of a convolution. We take our H of N, we flip it, we shift it, it's completely inside our signal, and we have to take those N2 H values and multiply them by their corresponding lined up input samples. So there's N2 multiplies. And so that's an N2 multiplies per output sample, but in this setting, for every input sample that comes in, I get 1 output sample. So that would also be the number of multiplies per input sample. So we end up with N2 multiplies there. And so now we need to compare them. So this thing on the left is the number of real multiplies for the overlap add, using all the assumptions that we made. And the thing on the right-hand side is the number of multiplies per input sample necessary to implement this directly in the time domain, whether it's via convolution or direct form 2 kind of thing. So from this, we can see that we need to look carefully at this inequality, which I've labeled star, and we need to choose NB. So for a given N2, so N2 is the size, the length of the filter that we're trying to implement, and it shows up in 3 different places. So for that given N2, we want to choose NB so that the left side is less than the right side, because that's when OLA is more efficient. And so to better see this, what we're going to do is divide both sides by N2. So if we divide both sides by N2, so take that and divide by N2, and then this gets changed to 1. So we'll compute that ratio on the left-hand side and look to see when is it less than 1 and when is it greater than 1, and how do we choose NB for various values of N2. So what we'll do is we'll make a plot of this for different values of N2 and for different values of NB, and we'll look at the result of this ratio. So a nice contour plot, which we can do in lab, allows us to do this. So each contour is nothing more than the ratio of the overlap add multiplies divided by the time domain multiplies. And remember, we want this to be less than 1, and our horizontal axis is the filter length N2, and the vertical axis is the block size NB. And we're ignoring the issues of powers of 2 and so forth. But if we look at that, we plot that as a contour plot. So imagine this is like a topographical map showing us a hillside. We can see that in this region over here we have contours that are bigger than 1. So let me get back over here and try to erase some of this. So I've highlighted with a red circle there the contour that is equal to 1. And so you can see that goes here. So that's our contour where that ratio is equal to 1. And everything in the upper right corner relative to that contour is going to be a ratio of less than 1. And everything to the left and below that curve will be ratios that are higher than 1. And one thing that we notice is that we can always choose a block size big enough to get up into numbers that are less than 1, as long as the filter length is about 19 or more. So if we look at this vertical line here that just kisses the 1 ratio curve, so pretty much if we have a filter of length 19, 20, something in that order, we're right on the boundary of whether it's better to do it OLA or direct time domain. The big thing that we see here is that the longer the filter, the better this scheme works, right? So we can also see that for a given filter length, if you draw a vertical line, say at a given filter length, so let's draw that vertical line, the contour that it just touches, that's going to be the optimal block size for that filter length, because anything a block size larger or smaller than that will take you in this direction of the curve. And so what we see here is that once we know what our filter length is, we can find the appropriate optimal block size. And we also can see that that block size is not real critical. It's kind of a flat curve, so I can kind of go over a fairly broad range of NB. And remember, this is on a log scale, so I'm actually going further than you might think when I do that. So this curve is showing us kind of the optimal block sizes as our filter length grows. The other thing that we can see is that as we as our filter length grows, that ratio gets smaller and smaller, right? It's down around 20, 30. We're at a ratio of about 0.8, 0.6. When we're out to filters that are in the 120, 140, we're down to 0.2. That means that the overlap add requires only 20% of the real multiplies that the direct time domain result or approach would need. So that's some pretty serious savings in complexity. And so that really points out the real potential of this algorithm. And so this is a really nice analysis here that shows how this works, and this is a great tool for you to know about. If you're implementing really long filters, this is a very important method to know about. So we'll stop there, and I'll see you in the next set of notes.